I think we finished with the PV manufacturers, and now we will enter into the perspective of the material suppliers. And when we talk about materials, I think metallization plays a very important role, irrespective of a technology, whether it is PERC, TOPCon, or more in heterojunction. So we have Mike Gu from DKEM. Mike is a new technology development director at leading pacemaker DKEM. He's going to talk about innovative metallization paste, enabling TOPCon efficiencies beyond 26.5%. Mike, we are very excited to see how we can increase the efficiency with metallization paste and also probably reduce costs.
Thank you, Shavin. I will share my Okay, can you see my screen?
Yeah.
Okay. Thanks, Thai News for the chance to help me share the DKEM latest progress on TOPCon metallization paste. And today my topic is innovative metallization paste enabling TOPCon efficiency beyond 26.5%. And first, please let me introduce DKEM first. And we are a material company founded in 2010 in China. And we focus on photovoltaic silver paste development. And also we provide electronic adhesive products for the semiconductor industry. And we are the first listed silver paste company in China A stock. And actually we are the major silver paste vendor in the global PV cell market. First, from the solar cell efficiency record, we can see with solar cell efficiency pushed to its theoretical limit from PERC to TOPCon, then to AJT, the VOC and the fill factor increasing significantly. The number of the VOC multiplied by FF is a key indicator of cell efficiency potential. And also, actually, it is the driving force for higher efficiency solar cell. To achieve higher VOC and FF, actually passivation technology is quite important. Especially that means a lot for the VOC. From standard P-type cell to PERC and then the TOPCon, the passivation materials in the process continually reduces the recombination and improve the VOC. And actually the development of passivation materials in the process is the key driving force to achieve higher VOC and the FF. Accompanied with the passivation upgrades, actually metallization paste also changed a lot in the past few years because essentially speaking, the fire-through paste actually directly etched through the passivation layer to form the ohmic contact. The paste and the passivation interaction is a balance between the recombination and the ohmic contact. As we all know, there are 4 kinds of contact models I think you are very familiar with. And from our perspective, the direct contact by model A and model B through the silver crystallites and direct contact between the silver crystallite and the silicon dominates the main contact mechanism. And that is the high efficient and the most high efficiency contact model and benefit a lot to the reducing the ohmic contact resistivity. At the N+ area, just like the story of PERC and TOPCon rear sides, the silver crystallites formed very easily because the silver ion can get electron easily from the N+ emitter. While at the TOPCon front side, due to the lack of the electron P+ emitter, the direct contact is pressed in pure silver paste. So to solve this dilemma, one solution is to adding aluminum to the silver paste that we all know as the silver aluminum paste. But the question is that at the same time we improve the contact. At the same time, the silver aluminum spike caused very high Gina metal because of the aluminum cans, and the silver spike sometimes can grow to micron level that will damage the junction and cause severe recombination at the front side surface. And also another way is to inject carrier externally, no matter by the electro carrier injection or the laser-induced carrier injection. Both show the improvement on the contact already, especially with the laser-enhanced contact optimization. As we all know, the laser-enhanced firing metallization method actually a very hot topic now. Already demonstrate a very good result on reducing the Gina metal and maintain the good contact at the same time. The laser enhanced firing process can work. Actually, a key reason is it decouple the metal-induced recombination and the contact in some level. The firing process usually focus on the Gina metal control, while the laser focus on the contact formation. When the silver aluminum paste nowadays starts to meet the bottleneck, the laser enhanced firing process pushes the balance of the VOC and the FF to a higher level. DKEM, actually, we start the study of the laser enhanced firing paste very early with an industry partner. And now we have the DK72E frontside finger, which demonstrate good performance on laser enhanced firing process. From the SEM picture, we can see after the laser enhanced firing process, when remove the glass layer and the silver bulk, the etching of the silicon pyramids, especially at the tips, is significantly improved with the standard silver aluminum paste. That indicates that the passivation layer is protected and we achieved less junction damage, which all benefit the VOC. With the on-site test data, we can see under the dropping condition with DK72E, 6 millivolt VOC gain, VOC is gained with slightly increased by FF. By reducing the peak firing temperature by 20 and even 40 degrees, the VOC can gain extra 2 millivolts with no obvious compromise of the FF. DK72E show good control on the Gina metal and very wide fire window at the same time. In terms of the contact, though actually by the laser enhanced firing process, we didn't get the efficiency gain directly. But actually the laser enhanced firing process do open some window to optimize the cell process for our customer. One possible point is the selective emitter. When we revisit the selective emitter technology on the laser enhanced firing process, here comes the question that can laser enhanced firing solve the contact issue on lightly doped emitter? If yes, less process depth and the less laser damage will surely benefit more VOC gain and reduce the cost. Luckily, by innovative inorganic recipe, the contact resistivity of the modified DK72E is further reduced, even though still slightly higher than on heavily doped emitter, but it's very close and significantly lower than the silver aluminum paste on the non-selective emitter area. There's still more work is ongoing actually, especially when the emitter goes to further shallower and extremely lightly doped. This sure will raise more challenge for the paste contact, even with the laser enhanced firing process. For the printability part, because on laser enhanced firing process, we no longer need lots of aluminum powder to form the contact. So reducing the aluminum powder also benefit printability, since the aluminum powder distribution and its dispersion in the silver aluminum paste is always a tricky question, which limit the screwing opening to go below 13 microns. Paste vehicle and together with the inorganic part optimization on DK72E already demonstrate better printability versus silver aluminum paste, especially on narrow screwing opening, like the 11.5 microns. Together with the advanced screwing technology like 8 micron diameters, mesh, and the 3D process actually already adopted by some cell makers in China, the less than 11 micron opening printing is expected. And another benefit from the aluminum reduction is gray line resistance. That's very obvious because after we remove the aluminum powder in the paste, the gray line resistance is greatly reduced. When further reducing the lay down and go to fine line printing, the lower gray line resistance will prevent too much FF loss and gives wider window to further reduce the cost and maintain the efficiency at the same time. And we also study the reliability of the DKEM2E on the laser enhanced firing process. As we all know, the silver aluminum paste showed worse reliability than the pure silver paste in PERC. One reason is that during the firing, the aluminum left more void in the finger gray line, which gives a tunnel for water to go to the glass layer. And also the electrochemical reaction with the aluminum and the silver accelerates the corrosion of the silver silicon interface. The dominant root cause is still the corrosion of the glass layer. Acetic acid test is usually used as a fast test to evaluate the reliability of the cell in the silver aluminum paste system. Interestingly, while on the laser enhanced firing process, when we compare the two totally different paste systems, we find that acetic acid test results show weak correlation with the PCT in both cell and the small module, and also different from the module, the complete module DH results. Even though the acetic acid result of DKEM2E is worse than the silver aluminum paste, as we see in the table, actually the cell and the module PCT of DKEM2E is much better. The FF degradation during the cell PCT test is significantly improved. And at the true application environment of the module, heat and damp are the main reason cause the failure of the cell. The low acetic acid will also impair the reliability, but the concentration of the acetic acid is much lower. And also this usually impair the cell at the later life cycle. And now we have more and more DH results coming out with the single glass and the double glass modules. All show that the reliability is much better than the silver aluminum paste. So I think by this result, we need to revisit the rationality of the acetic acid treatment condition, especially at the cell level. We talk about when we talk about the laser enhanced firing process, maybe we mainly focus on the front side fingers, but actually for the rear side on laser enhanced process, we have some new findings that it may raise a different requirement for the rear side fingers. And for the laser enhanced process, firing process, we have the specially designed rear side finger paste DK95E. The DK95E, it inherited the wide process window of DK93T, which already demonstrated by the market to match well with different TOPCon process, like the different aluminum oxide process and the different poly deposition process and the different texturing process. And another aspect, considering the laser enhanced process, we also improve the contact at the rear side by some level. The modified DK95E can support customer to go to the further thinner polysilicon. On standard firing process, when goes to the thinner poly, without special design recipe, the size of the silver crystallized from during the firing can go to more than 100 nanometers, which will damage the polysilicon if the thickness of the polysilicon is below 100 nanometers. This will cause the high G-non metal. Also, with the thinner poly, the lower doping concentration also raise the contact resistivity significantly. By innovative inorganic system optimization, the DK95E, together with the front side laser enhanced firing process, can control the size of the silver crystallized precisely, allows customer to go to the thinner poly below 100 nanometers, and significantly reduce the G-non metal and improve the contact resistivity. Even though the passivation quality may be compromised and the implied VOC might be decreased, after metallization, we can still see the efficiency gain. mainly from the VOC and IESC, just like we showed in this table. This phase actually is already in mass production at customer site with 80 nanometers PE poly with demonstrate process stability and efficiency benefit. Under the laser enhanced firing process, usually our customer will reduce the firing temperature for more efficiency gain. While this will impact the busbar adhesion at both front side and the rear side. The busbar adhesion actually became the bottleneck for high efficiency at some customers. We developed the DKA2E busbar paste, specially designed for the laser enhanced firing process. The DKA2E busbar paste can maintain very high adhesion and also the aging adhesion, even with more than 60 degrees lower firing temperature. This further enlarged the fire window to help customer gain more efficiency benefit from the laser enhanced firing. And also with the ultra floating design, the DKA2E showed the low recombination and low busbar finger interaction, which reducing the busbar dark EL issue at some special customers, and that will help customer to increase the production yield. In these slides, I will talk about the bifacial poly. From the passivation point of view, the bifacial poly TOPCon is expected to be the next generation cell to further reduce the recombination at both front side and the rear side. The N polysilicon and the P polysilicon on bifacial TOPCon raised a new requirement for the paste. For the front side N polysilicon, due to the texturing surface, the passivation layer is more easily to etch through at the pyramid tips. Usually cause higher J-nanometer metal compared to TOPCon rear side polished surface. Also, considering the parasite absorption of the polysilicon, usually customer would like to go to the thinner front side N poly, and also needs to control the width of the poly finger. When customer goes to the thinner polysilicon, it is very important to control the size of the silver crystallites, especially at the pyramid tips. And also, when customer go to the narrower poly finger, we need to continue to narrow the finger gray line. And the fine line is actually raise the higher and the new requirements for the N poly finger paste. And for the rear side, because the rear side P poly, considering the poly thickness is much thinner than the P plus emitter, which is usually for P plus emitter with the SE scope can go to the 2 microns, and without SE maybe more than 800 nanometers. But the P poly is already below 300 nanometers. So at the rear side P poly, the pure silver paste is needed to match the P poly process. If we add aluminum in the paste, that will cause very high J-nanometer metal at the P poly side. So this raised the requirement of the raised very high requirement for the pure silver paste on the P poly contact, especially when combined with the polished surface and the aluminum oxide silicon nitride stack layer. Our P poly paste DK73K paste can achieve similar contact resistivity level with the silver aluminum paste on the P plus emitter. And the bifacial TOPCon, we have provided the total package for the front side is DK95B and the rear side DK73K showed more than 0.1% efficiency benefit versus some other paste vendors on the bifacial poly TOPCon structure. So to summarize, actually nowadays the laser enhanced firing process further raise the VOC and the FF of the TOPCon, which will become the new technology platform in the 2024. And for the bifacial poly TOPCon as the next generation cell to further improve the VOC is also in development by some customers. And as a main paste vendor, DKEM would like to work together with the industry partners to develop the paste for all kinds of the new structures and further to improve the efficiency on TOPCon. Okay, thanks for your attention, and that's my presentation.
Okay, thank you very much, Mike. So, you know, I have a few questions here. You know, with the TOPCon, there are basically three routes. So PVD based TOPCon, PCVD, and LPCVD. So will there be any difference? Of course, this process is on the front side. So is it going to impact what kind of process route you are taking for TOPCon with this laser assisted firing process?
Actually, for different polysilicon deposition technologies, no matter PECVD or LPCVD, mainly it impact the rear side paste development.
Right.
For the front side, actually, usually this have little impact on the front side paste recipe, especially under the laser enhanced firing process. Because by the data we collected now, the laser enhanced firing process, in some level, it's reduced the contact requirements on the front side. So different recipe make the gap of the different recipe on the front side, especially in terms of the contact resistivity, we can go to the gap can go to very close. So maybe the different deposition of the rear side poly still raise the higher requirement for the rear side paste, but till now we didn't find very obvious the difference on the front side silver paste development, and mainly it's related to the boron emitter doping and the different passivation layer. Yeah, that is the impact to the front side finger paste more.
Okay. So the special paste with the laser based process, can it also be applied to the bifacial poly, or is it mostly for the the traditional TOPCon structure?
Yeah, actually, that's a very good question because we are still developing the specially designed paste for the bifacial poly. Because right now the paste, especially at the P poly, the bottleneck of the P poly contact is the contact resistivity, and the laser enhanced firing process just can solve the contact issue. So we are developing some paste, especially on the P-type poly. We have some good data on that, but still because it's highly it's very very early stage, so we are not putting in these slides. I'm sure there will be some special design paste for that process.
Yeah. So since the topic is really so hot, please allow me for two more questions. So one thing is, so how is the paste consumption? Because now is this also paves a path to reduce the silver consumption, which is of course directly correlates to the cost, right? So can you say what would be the silver consumption for the fingers compared to the traditional TOPCon contacting paste and the laser enhanced paste?
Actually, because the laser enhanced firing process just starts mass production recently, so most of the cell makers, they didn't go to a very extreme narrow screen opening. So the laydown right now is similar to the standard silver aluminum paste. But I believe in the recent future, when customer goes to narrow finger screen openings, the laydown can go to even lower, and also because the whole process reduce the requirement of the contacts, no matter on the front side or no matter on the rear side. So it's for sure that will open more window further reduce the laydown, because right now reducing the laydown not only the gray line resistance is a bottleneck, but also the contact resistivity, especially at the rear side, is also the bottleneck. So for the laydown, further reducing the laydown, we also benefit from this process. That's for sure.
Okay. So can you say regarding the complexity of the equipment, what you would like, what you need to implement the laser-assisted firing process in a typical production run? So is it like simple laser, or can you say some more details?
Sorry, you mean the?
Yeah, so the equipment, so it is not just like, you can do it in a firing furnace. You probably also need some laser equipment, right? So how technically advanced the laser equipment should be to accomplish this process on the capital expenditure, CapEx?
Actually, the laser didn't. We didn't pick different laser to match our paste. Actually, right now we find some different equipment vendors. Their laser are different and their equipment are different, and that may cause a different effect on the final efficiency gain. Some equipment may benefit VOC more, some equipment may benefit the FF more. But now our paste can match all the different equipment. But for sure, I think when the process goes to even more precisely, and the paste will develop according to different equipment. Just like right now, we develop the rear side paste according to different polysilicon deposition process. And for sure, in the past few months, we will develop different paste according to different equipment and according to different lasers. Yeah.
Okay, so thank you very much for sharing these exciting results and a pathway for TOPCon to become even more efficient, probably much more than what we see today. So thank you very much for sharing this work. And I think there are also a few questions in the chat window. So please try to stay back and enjoy our conference while answering these questions. And I'm sure they might pop up even more.
No problem. Thank you, Charlotte.